meant to ever set up a technical university outside of Germany. So it was a rather big project. Indian officials approached German officials whether they could help them to set up a technical education institution, because Germany had a very good reputation for technical education, but then this was more like a partnership. If you want to know what was different between IIT Madras and the other IITs, so workshop education and the workshop component was very strong. Until the 90s, there were continuing collaboration projects or like partnership projects, which meant that there were a lot of scientists coming to IIT Madras and also a lot of Indian scientists being trained in Germany. We have still a very, very strong German collaboration. So we have the Indo-German Center for Sustainability. Also very interesting to see IIT Madras in a longer history of Indo-German relationships, and specifically also Indo-German relationships in the history of science and technology.
Talking about consumer electronics, every time you use a mobile phone, it makes use of an analog mixed signal IC design, which IIT Madras has the most leading centers for. The world of tomorrow is going to be more electric driven than it is today. And that leading edge technology is being created right now in IIT Madras.
The Institute of Eminence scheme has been launched by the Government of India to empower higher educational institutions and help them become world-class teaching and research institutions. IIT Madras is proud to have been selected as one of the select institutes of excellence. As part of our commitment to the cause of fostering world-class research, IIT Madras has set up a number of research initiatives in diverse fields of contemporary relevance. Many of these initiatives will go on to become centers of excellence within the IIT Madras system. A total of 68 research initiatives belonging to 21 identified technology clusters are presently underway. As part of these initiatives, it is proposed to host a series of webinars from each cluster to showcase the innovative research being generated to various stakeholders like researchers, industrialists, and policymakers. These webinars will give an opportunity to engage in conversation with eminent faculty from IIT Madras and other international researchers, and also to find more collaboration in those research areas. So why wait? Click the link below to be a part of this.
The campus is very clean and the environment is highly protected, so it is acting as a lung of the Chennai city. This is a biodiversity hub. We have around 1,000 various species present in our campus. We have around 100 different species of trees. Out of that one, 40% or 40 are native trees and 60 are foreign. We have very active environmental group.
This is the powerhouse where the foremost innovators and entrepreneurs of the country team up with the smartest talent pool of students and faculty from IITM.
Hello and good day to everyone. Thank you for joining us today. On behalf of the Office of Global Engagement, it is my pleasure to welcome you to the 45th webinar from the IRIS webinar series. My name is Richard George Philip and I'm a part of the Office of Global Engagement. The Institute of Eminence scheme was launched by the Government of India to empower higher educational institutions and help them become world-class teaching and research institutions. IIT Madras is proud to have been selected as one such Institute of Eminence. IIT Madras has been, IIT Madras has been ranked as the #1 institute in India in both overall and engineering categories in NIR of 2021. IIT Madras has bagged the top rank in overall category for the 3rd consecutive year and #1 in engineering category for the 6th consecutive year. In the newly launched category of research institutions, IIT Madras has been ranked #2 in the country. A total of 68 research initiatives belonging to 21 identified technology clusters are presently underway at IIT Madras. As a part of these initiatives, the IRIS webinar series aims to showcase the innovative research being generated to various stakeholders like the students, researchers, industrialists, and policymakers. And from the Quantum Science and Technology Cluster, the research initiative presenting today is titled Quantum Centers in Diamond and Emergent Materials, led by Professor M.S. Ramchandra Rao. At this center, they explore the quantum world from phenomenology to technology for computing, communication, and more through materials like diamond to realize qubits, superconductivity, and meteorology, unraveling emergent phenomena and explore quantum physics. To introduce Professor M.S. Ramchandra Rao, he is a professor of physics and an institute chair professor at IIT Madras. He obtained his PhD from IIT Kharagpur and has been a recipient of several prestigious fellowships and awards, including the Humboldt Fellowship, JSPS Fellowship, and serves on the editorial board of the Journal of Physics D, Institute of Physics. His research is focused on diamond and emergent quantum materials. In particular, he specializes on thin films, pulsed laser deposition, oxide electronics, magnetotransport studies, and spintronics. Joining us as the speakers today are Professor Vidya Praveen Balamudi, Professor Shantanu Mukherjee, Professor Shivaramakrishna, and Professor K.G. Pradeep. Professor Vidya Praveen Balamudi is an assistant professor of physics at IIT Madras. His broad interests are in the areas of quantum technologies using defect centers in solid-state materials and nanoscale magnetic spectroscopy and imaging. His expertise is in optical and scanned probe microscopies and magnetic resonance studies. Along with his collaborators, he pioneered a technique for gigahertz range spectroscopy of ferromagnets using NV center quantum defects in diamond. Professor Shantanu is an assistant professor of physics at IIT Madras. He is a theoretical physicist who studies various aspects of condensed matter physics, including strongly correlated systems through advanced methods. His interests lie in understanding superconductivity and quantum spin Hall effect in low-dimensional systems such as atomically thin materials as well as conventional systems. Professor Shivaramakrishna is an associate professor in physics at IIT Madras and heads a Max Planck partner group. His group specializes in light-matter interaction involving quantum and X-ray aspects. The key highlight of this research is unraveling correlated and collective phenomena in quantum systems from the angstrom to nanoscale, combining spectral and time-resolved probes from the near-infrared to X-rays. He was nominated to lead a Max Planck partner group and has won several national competitive grants, as well as beam times at international facilities like Electra, Trieste, and DESY Hamburg. Dr. K.G. Pradeep is currently assistant professor in the Department of Metallurgy and Materials Engineering at IIT Madras. He completed his PhD from Max Planck and RWTH Aachen University, Germany in 2014. Prior to joining IIT Madras, he was the group leader for atom probe tomography at RWTH Aachen University. His expertise lies in the fields of alloy design, correlative microscopy, and combinatorial approaches. He has published 58 peer-reviewed journal publications in the field of physical metallurgy, magnetic materials, atomic scale microscopy with a H index of 24. He is currently the coordinator of National Facility for Atom Probe Tomography at IIT Madras. It is my pleasure to finally introduce the moderator for the webinar today. Professor Werner Paulus is with us today. Professor Werner is a professor at the Institut Charles Genhardt, University of Montpellier, France. He is a leading expert in X-ray crystallography and neutron scattering, which he applies to advanced quantum materials, including perovskites, stoichiometric oxides to realize novel functionalities, including spin and magnetism-based technologies, quantum defects in low-temperature phenomena. His group particularly emphasizes multifunctionality of materials, applying these to energy conversion, sensors and actuators, electronics, and more. He has contributed many innovative approaches to this field and is well known for his contributions. He leads the Europe-wide MA-MASc Masters program, mentoring of young researchers in this field, influencing upcoming generations. Thank you for being with us, Professor Werner, today. We're very excited that you could be a part of this session. We also have a very distinguished panel members from various departments at IIT Madras. We have Professors Dr. Yasir Iqbal, Dr. Panchanana Kuntia, Dr. N. Arunachalam, Dr. K. Setupati, Dr. G.L. Ganapati, Dr. Basdev Roy, Dr. G. Bhaskaran, and Dr. Satyan Subbaya with us today. A warm welcome to all of you and all of the participants here. So before we start, a quick note to the participants, please use the Q&A box to enter your questions and upvote questions that interest you so that the moderator can prioritize them later. Over to you, Professor Ramchandra Rao.
Thank you, Ms. Richu, for a nice introduction. So a very good afternoon or good evening to all the participants, and a warm welcome to our entire team of our center, QuCenDiEM. As the introduction has been done to the center, the name of our center is Quantum Center for Diamond and Emergent Materials. So today, in the next 1 hour, we're going to share all the excitement that we're going through various aspects of quantum materials and quantum technologies with you. So the motivation and the genesis of the center is, we have a holistic approach towards materials and quantum technologies. We believe that materials is the key. The hardware part is very essential if you want to go all the way to technology. So what you see on the left side is, we work on quantum materials development, their synthesis, growth, backed up with a very strong theory, and demonstration of quantum control and measurements are absolutely important. The device development thereafter for detection, imaging, and spectroscopy, and the development of hybrid quantum systems. So this is our wonderful team of faculty members from physics department with strong theoretical and experimental backgrounds. We also have colleagues from mechanical engineering department and metallurgical and materials engineering departments. So it's a nice team working on 4 to 5 different verticals related to diamond and emergent materials. I know there are a lot of young students sitting in the audience, so let me start as a teacher. Let me spend a few minutes on some basic concepts. Let's look at the fascinating world of physics. It's such a big ocean with so many interesting fields. All that we learn from our school days to college days to university, electromagnetism, the thermodynamics, classical mechanics, and high energy physics, of course, is a very fascinating field. Theory of relativity, atomic and molecular physics. We have seen the discovery, 50 years of discovery of laser a few years back. And then you have this very exciting field called astrophysics. And of course, quantum mechanics is indispensable. Without quantum mechanics, you cannot understand anything about quantum materials. So the fields that we work on are related to one part of this big ocean, that is condensed matter physics. And in that, physics of low dimensional systems. So you take condensed matter, solid state matter, and exhibiting various properties like superconductivity, magnetism, semiconduction. And what happens to this solid state matter when you take them, when you cut the size of these solid state materials to nanometric scale? So the physics of low dimensional systems is called nanoscience. And those nanomaterials exhibiting interesting quantum properties, we can term them as the quantum materials. I like this slide always because it summarizes 100 years of our great history in science and technology. and the discoveries that I have mentioned here, and the people who have received Nobel Prizes, all these discoveries have something to do with quantum phenomena. Well, at the beginning of the 20th century, when most of the scientists felt that atoms are just abstract quantities used for the purpose of calculations, it was Albert Einstein, through his wonderful paper in 1905, which was later translated into English, clearly said that, this paper was on the Brownian movement of particles based on the molecular kinetic theory of heat. He clearly said that, look, atoms are not abstract quantities. They have to be real entities. It's just that at that point in time, there is no way to prove the existence of atoms. See, what a visionary he is. On this, the one on the left-hand side top, that the greatest physics teacher of all times, Richard Feynman, even in his 1959 Caltech lecture, he talked about how to write small rearrangement of atoms. This is happening now. We can manipulate atoms using lasers. He talked about marvelous biological systems. And then these two are really great visionaries of physics. And in 1961, this invention has changed many things, the Josephson effect. And in fact, the Josephson effect that has led to a lot of understanding on the process of quantum mechanical tunneling, has been used to, invent an equipment called scanning tunneling microscope. It's very rare that an experimental invention gets a Nobel Prize. And because of the value attached to this invention, these two scientists got a Nobel Prize within 4 years after its invention, because it has completely changed the course of nanosciences and quantum sciences that we are dealing with today. And today, using this simple equipment, we can actually map the atoms. You see that? This is the real space imaging. Diffraction gives you information about reciprocal space of the material. You get information back about the real space lattice. But here is an image of a real space imaging of a crystal. But then today we have gone far beyond that. A colleague of mine will elaborate on that. This is an image of atom probe tomography, where you can also get about the chemical environment of the atoms also. And you see a perfect periodic arrangement with some defects seen there. That's the kind of sophistication that we are seeing nowadays with the experimental tools that we have. Well, modern physics came of the age in the beginning of 1900, and then physicists discovered that Newtonian mechanics did not work when the objects were very small or when they moved fast. If things are confined to, say, very small dimensions, nanometric scale, then quantum mechanics is absolutely necessary. So we talk about atomic orbitals, quantization, quantum metastructures, quantum wells, etc. So the first part of our presentation that we deal with is about diamond, and defects in diamond. We can call them quantum centers, and you can do rich physics with these defects in a diamond, artificially induced defects, and you can envisage many applications. And then you'll be seeing a large number of very fascinating emergent quantum materials. Some of my other colleagues will speak about all this. Unconventional quantum phases, 3D frustrated quantum magnets, quantum spin liquids, etc. By the way, that diamond was mined in India 4,000 years ago, but 4,000 years ago, no one knew what its structure was, even though a lot of value was associated with diamond. We know diamond is the most expensive crystal. So when did we come to know of its crystal structure? We know that diamond is just made up of carbon atoms. It's only about 100 years back with the advent of crystallography, the advent of X-rays. So we celebrated 100 years of crystallography a few years back. So this is, again, to emphasize the need for X-ray crystallography when you're dealing with material processes and material technology. Okay. So QuCenDiEM, what do we do here? We talk about diamond growth for quantum diamond, emergent materials, and quantum X-ray photonics and lasers. And a part of it I'll talk about now is the growth aspects of diamond. It's a very fascinating material. It's an insulator to start with. Diamond is one of the best insulators. The separation between the valence and conduction bands is about 5 electron volts, but you can tune the conductivity by doping. right? And then in nitrogen doped diamond, you can do very exciting physics. So we deal with all these things, device aspects, and also some of my colleagues, they look at the fabrication aspects of diamond using these heterostructures for sensors and other applications. A plethora of applications this material has. You can use diamond coatings as hard coatings to prevent materials from wearing out. A lot of applications in aerospace for defense, in the fields of defense and aerospace applications there. Diamond has the highest thermal conductivity, 4 times more than that of copper. So you can use it as a thermal spreader. You can use diamond electrodes for water purification, and also, of course, I mentioned that quantum applications, plenty of them. A few more applications here. Diamond coatings are also biocompatible, so there are lots of medical applications. You can use diamond coatings as optical windows because diamond can cut off radiation from mid-UV all the way to gamma rays. So you see there are about a dozen different useful applications, including water purification. These are great societal applications that we are looking at. Now, this small video clip, this is a unit that is used for creating diamond. This is a hot filament CVD. The name itself suggests that you have hot filaments, tungsten filaments heated to almost up to 2,300 degrees centigrade, and methane is a gas there, the precursor gas. And then you see the formation of diamond on the substrates that are kept at a distance below the, these hot wires, made of tungsten. What you see on the right-hand side is a small, interesting clipping of you have 2 substrates there, one diamond coated on silicon, and the same diamond with the boron incorporated into the lattice. And you see what happens. The first one is when you just bring those 2 multimeter probes, you see an overload here. That means the resistivity or resistance is very high in gigaohms, right? It's beyond the limit of this meter. But then the moment a small amount of boron is doped in it, 3 to 5 mole%, you see that. So the gigaohm resistance drops down to a few tens of ohms. This is really beautiful, right? Because this is the power of doping in a lattice like diamond. Same thing happens in most of the semiconductors also. So the resistance that changes significantly with boron doping, right? If you measure the resistance now all the way down to the lowest possible temperature, you start seeing superconductivity in this. So there's diamond superconductor. So an insulator, upon doping, it acquires a semiconducting property, metallic property, and then finally it becomes a superconductor. But of course at 6K. So then you do the same resistivity measurement in the presence of high magnetic field, varying the field all the way from 0 Tesla to 5 Tesla. Superconductivity doesn't vanish, which means this property indicates that you have a high degree of granularity there. And that is the crux of utilizing boron-doped diamond for many quantum information applications. I'll come to that in a minute. The second part is we also dope diamond with nitrogen. It's not easy, these things, you need to dope these materials. You need to do a lot of characterization. Nitrogen can be doped with only implantation. You implant these nitrogen ions and then anneal the sample, and then you get nitrogen getting into the lattice, giving rise to 1 electron. And it also creates a vacancy. So these nitrogen vacancies are the fundamental elements for quantum bit fabrication. So these are called NV centers. NV centers are basically artificial atoms in the crystal. They have perfectly stable luminescence at room temperature, leading to very efficient, practical single photon sources. And their electron spin can be optically detected and manipulated by magnetic resonance techniques. Okay, now you see that. This is one of the latest papers we got with a group from University of Maryland at College Park. this is very exciting because in the last 3 decades, lots of superconducting systems have been tried for many quantum impedance device applications that are used in microwave circuitry. But the condition is, even though we have hundreds of superconductors available, you need superconductors that are granular. So for example, you have aluminum in the form of a granular superconductor that has been used, niobium nitride and titanium nitride. But then it is turning out that boron-doped diamond, in which we see superconductivity, shows the largest microwave kinetic inductance, which means it opens up a new area, in microwave circuits, where so-called high impedance quantum circuits and current tunable delay lines. So this is one of the main applications of boron-doped diamond. And now about the nitrogen vacancy part, what we can do with that, my colleague Praveen will take over.
Hi, Masar. Thank you for that very nice introduction. And so I'm glad students are getting a bit of the evolution of how we are coming along to the quantum aspects of things. Obviously, there were quantum technologies such as superconductivity, that one that Professor Ramchandra Rao talked about. And so this is the next generation that we are going to be talking about of quantum technologies. And this pretty much impacts most or at least it's envisioned to impact most our lives across many different spheres, from across the way, from computing to sensing to communications to simulations. And within this different clusters at IIT Madras, you may have heard some of the other talks more dealing with computing or communications. In this cluster, or in this COE, we are more focused on the sensing aspects. And when we say quantum technologies that are emerging right now, the key for people to understand is the kind of resources that quantum world gives us, which is what we plan to use. And some of these words you may have heard, and again, in the interest of time, we won't have time to go into much detail probably in this kind of presentation, but I hope students get motivated to look up themselves and pursue this as their careers. So superposition, entanglement, teleportation, and quantum noise. And of course, there are existing ones like superconductivity that have already been used, tunneling devices, which again exist, tunnel devices. So these are the kind of resources that we are planning on using. And so the way we plan to use this is, first is, of course, we need to find a quantum system. And the particular quantum system of interest, let's say I'll give you one example in our case, now it's sort of becoming a canonical quantum system called as nitrogen vacancy center in diamond. And as you can see the arrow that, so this is a center. So first thing to understand is that pure materials are not always the best. We need to have defective materials. And as Professor Rao had also talked about showing defects and, in one of the TEM images, similarly here you can see that we are doing doping again, much like silicon is doped with phosphorus or, boron to create PN type of diamond, PN type of silicon. Here we have one nitrogen, but this defect also includes a vacancy. So when a nitrogen and a vacancy, which basically means an absence of carbon, they come together, this is what makes diamond pink if you dope it, if you create enough of these vacancies. But typically we deal with much lesser, in the order of parts per billion or parts per million at most. But the key idea is, if you do manage to create these artificial atoms, which is what these defects act as, then you will have a very nice two-level stable quantum system, okay? And this two-level quantum system, so you can look in the middle panel, the advantage of this two-level system is it's fairly stable, and you can use laser light. You can use a green light to initialize the quantum state to a very high fidelity. You can manipulate it using microwaves. And these microwaves typically of the order of gigahertz, you can use them to manipulate. And the one big advantage of this is what makes is that coherence time, which is the quantum lifetime that you can talk about, that is among the largest for a solid state material. And all of this put together allows you to look at quantum phenomena even at room temperature, which is kind of very cool. And that's really the driving force for people to look at these NV centers. And the very nice thing again is you can do optical initialization of these, or optical readout. And the way you can look at it is also by looking at the fluorescence intensity. So what you can do is what is called optically detected magnetic resonance. So if you look at the fluorescence intensity, which is the amount of red light or pink light, you can think, that is coming out of these defects, if you look at what happens as you apply a particular microwave, you will see the different spin states. If it is in spin 0 state, then it has high intensity of light coming out of it. Or if it is in plus or minus 1 state, which are different spin states or different quantum state, then it has different light intensity coming at it. And so with this, you can do very high, at the nanoscale, at the limit of a single atom, you can read out the quantum state, and which is very tough to do normally. And this is what this material allows you to do. And so to look at the kind of things that you can do with this, it has many different applications, some of which I have listed here. So one of the big things that motivated people to look at it is to look at it for magnetic resonance imaging. So all of you probably have heard of MRI, which is, a clinical tool nowadays, but this works at, resolution of hundreds of microns. If you want to take this to nanoscale where you want to study single DNA molecules or single cells, then you need a technique, like you need some different kind of detectors than what exists today. And this is what the NV centers provide you. It has a lot of applications for quantum computing, other kinds of sensing like nanoscale temperature sensing. Again, in your body, in your cell, different processes can change the temperature if you want to study them. If you want to study electric fields at the nanoscale, all of these things you can, it's a combination that it gives you between nanoscale sensitivity, nanoscale resolution with high sensitivity. And so there are these various things that you can do with this. And this is what I'm illustrating some examples from literature to highlight the power of this technique. And as I said, what it brings about is an unprecedented combination of spatial resolution, which is down to almost, as you can see in the first figure, reaching almost angstrom level or atomic scale level with very high signal sensitivity. So what you're seeing there is magnetic resonance imaging of individual nuclei. That is where people have mapped within a diamond crystal with angstrom scale resolution. Of course, this is stuff that is being done around the world. We are not quite there yet, and so we have lots of work to do in this particular project. But nonetheless, that's the power of what we can do. In the middle, you're seeing similarly nanoscale magnetic resonance imaging. This is magnetic imaging of ferromagnetic materials. Ferromagnets play a lot of interesting roles in your technology that you may not be aware of, but nonetheless, they do play. And so this is kind of looking at magnetic imaging at the nanoscale. The third panel that you see is looking at, in this particular work that I was involved with, where we have attached a nanodiamond, which is a tiny crystal of diamond, to a DNA molecule. And the goal is to try to understand the dynamics of DNA molecules, which is very important in understanding their functionality in your body. So these are the different kinds of things that you can hope to study. And this is what we are trying to build up to. And so that's the idea. And of course, but before building up to that, you first need to have a way of creating high quality materials, because if you don't have high quality materials, you can't go really too far with this kind of technology or even understanding the science. And so this is where we are building up right now. So we are trying to grow this. So Professor Rao is an expert in materials and growth of diamond. So we are trying to now move to single crystal diamonds and characterizing them. So we have to characterize first the quality of the diamond itself, and then also how to control the dopants, how to control the defects. So defects are important, but you need to have very precise control on them. And so there are different various techniques that we are trying to, we bring to the front for that. Of course, once you have the material, and you can do some science with that, the kind of science that I talked a couple of slides earlier. But when you want to move to devices, then you need to be able to structure them. You need to be able to build devices. This will require you to structure them in some ways. And there's again the advantage of diamond that is compatible with solid state techniques that were brought upon by silicon technology. And so we are using this in this case, focused ion beam imaging of diamond. So we have created nano pillars. And so there's a technique called as focused ion beam. And so what you'll see here is that these pillars that we are creating, which enable us to capture the light from the diamond with very high efficiency, You can create them, but I have put them on scale of a human hair. So that's a human hair. So these images are captured by something called a scanning electron microscope. And you can see these pillars, which are of the order of, approaching less than a micron. And if you put them on a human hair, that's the scale to give you an idea of what the kind of things we are trying to create. And so, but this is the kind of technology you need, from materials to being able to create structures in them, to be able to do the nice science and then the devices that we want. So yeah, so there, of course, another very impressive kind of technology that we are building, and Professor Shiv Ramakrishnan will talk about this later, where we are using lasers to both do two things. One is creating structures within the diamond, and the second part we are trying to do is also create these defects within them. But the nice part is we are using lasers. These are called femtosecond lasers. Again, the whole game is about precise control on what you're putting into the diamond to control the process. And we are controlling it down to femtoseconds. And so you have laser pulses down to femtoseconds, and if you can control them, then you can create both these defects and you can also create these patterns. And so that's again the kind of stuff we are trying to do. So that with that, I will hand it over to Professor Rao again, and he will introduce the next portion. And thank you.
Thank you, Praveen. Just a few lines about this. We'll come back to this slide with a little more description from my colleague later. We also make these single crystalline, polycrystalline, and doped diamond films membrane for structuring, nanostructuring, and patterning for various device applications that you see on the right-hand side bottom. I'll come back to that a little later. Just to show you that during the growth process, we can control the growth from all the way from microcrystalline diamond and nanocrystalline diamond, and the BDD stands for boron doped diamond, and that's how one can tune the microstructure and properties during the growth itself, right? So leading to then all those device architectures. All right. So before we move on to the exciting part of emergent materials, I'd just like you to go through some of the articles that are published in this particular special issue of Journal of Physics Day on quantum materials and quantum phenomena. There's so much happening on qubits, teleportation, quantum sensors, many body interactions, entanglement, spin-orbit interactions, wild semi-metals. Some of these aspects my colleague Shantanu will be talking about now. Shantanu.
Thank you, Professor Rao. So what I wanted to tell you about was about one of the subgroups within our QuCenDiEM Center, and that works on the theoretical and experimental understanding of quantum materials and their associated emergent properties. So when I talk about quantum materials, the term quantum material has generally come to symbolize material systems whose properties cannot be characterized by either semi-classical models or basic quantum mechanics. The quantum material, the amount of quantum material that exists, if you define a material as different from another material by virtue of its difference in properties, the excitement occurs along what Professor Rao was talking about, that if you dope a particular material, within this business of studying quantum materials, we actually look at that material as a totally separate material, because you could just dope a material with certain dopant, and what is a magnet at one dopant could end up being a superconductor, or what is a magnet of one type could end up becoming a magnet of another type, or you could have electronic orders. All sorts of novel phases could happen with doping. And it's not just doping. With the advancement in technologies, we can slice these materials to smaller and smaller dimension. You talk about 3-dimensional materials, 2-dimensional materials, 1-dimensional quantum materials. And at each of these dimensional reductions, you find entirely new exciting emergent properties. So if I might go to the previous slide, Professor Rao. Where you see the circle of the quantum materials, the figure shows the various phases of quantum matter that our group members are engaged in exploring. what makes these quantum materials complex, but at the same time fascinating, are their rich phase diagram, where multiple emergent orders or interactions are coupled. Right? So the possibility of tuning these emergent orders, so if you could have some handle of how you tune these emergent orders, which are coupled to each other, using such couplings or external perturbations makes them a rich testbed for development of material for future technologies. For example, you could take a topological quantum spin-Hall insulator, and you could tune the topological insulating phase to a topological trivial phase, as it is called, by using a bias voltage or electric field. Or you could take a charge density wave order in a certain quantum material, and you can tune it with a magnetic field. So understanding the microscopic origin of these various orders and developing theoretical models that could allow us to predict or explain this complex phase diagram of and the emergent properties is an important area of interest of our research center. So let us now look at some of the individual research interests of the members working on the emergent properties. So first I go over to the work of Dr. Panchanan Khuntia, who has expertise in various experimental techniques used to study strong correlation physics. So Professor Khuntia focuses on the design and growth of the paradigmatic frustrated magnets, including Kagome, hyperkagome, pyrochlore, and honeycomb lattices, wherein quantum effects are at play. They employ what are called the state-of-the-art techniques, including nuclear magnetic resonance measurements often done at low temperatures and high magnetic field, or muon spin resonance experiments, inelastic neutron experiments, and advanced thermodynamics to probe these novel quantum states and the elusive elementary excitations of these quantum materials at a complementary scale. So his group intends, what they plan to do with these experiments are they want to explore the collective quantum phenomena and the associated exotic excitations, so that it can reveal certain clues which will give us some understanding of what are the phases that form in these materials, these novel phases, and what are the microscopic origin. Because to be able to tune them, to have a tunable system, first and foremost requirement is to understand how do they occur. So the excitement is actually that for many of these quantum materials, we don't really understand all the details of the nuts and bolts of the microscopic physics. So if I go over to the next slide, just to give you an idea about one of the interesting areas of this frustrated magnets. If you look at the top triangular picture, for those of you who are new to this business, magnetism is generally associated with presence of unpaired spins at certain lattice site, and a long range order requires some exchange coupling between the spins to tell each other which way to point, right? Some moment at each side by itself is not going to lead to magnetic order. So they talk to each other. Now imagine that you have three sides on the triangle. If the exchange coupling wants to tell the nearest neighbor spins to point in opposite direction, which could be called as antiferromagnetic ordering, the problem with this triangle is that the third spin will be frustrated since it does not know which way to point. One of the spins which is there on the top wants it to point downwards, and the other spin which is on the bottom left wants it to point upwards. So this site has got a frustrated magnetic moment. Why this is exciting, this is one of the newer areas of research, is that this kind of frustration leads to very novel phenomena that are being observed in these systems. And a lot of theoretical and experimental work is going on to understand the origin of this frustration and the behavior of these frustrated magnetic systems. And these can occur even in square lattices and various other materials, depending on the exchange couplings that exist. So if I now go ahead to our next speaker, this is the next speaker. The next person, part of our subgroup is Dr. Yasser Iqbal, and he uses a number of novel theoretical techniques like variational Monte Carlo, functional renormalization group, to explore the origin of these exotic states of matter, like these quantum spin liquids. So effectively, you can think that when a magnetic order has not formed because of frustration in these systems, all the way down to zero temperature, you could have the situation that the fluctuations in the system could be various, could be quite large, but the system wants to order in a certain way. So the fluctuations are not entirely random, but yet they have not formed a long range order. So you get a new state, entirely new state of matter in these type of systems, what are called as quantum spin liquids. So the Dr. Iqbal studies essentially how these quantum spin liquids forms. And by using these methods, he explores that how would you effectively, let's say you start off with a Hamiltonian that describes one of these real materials. He would use various techniques and calculate quantities like spectral function and so on. And he'll make predictions which can be verified by people who work on, for example, inelastic neutron scattering or low temperature thermodynamics to see whether kind of the theoretical model is able to explain those experiments. So if I move on, just to give you a little more detail of Professor Iqbal's work. So as an example, as you see in this picture out here, he's working on, so if I talk about a little specialized language, he's working on developing what is called as a pseudo-fermion functional renormalization group framework on the real frequency axis, for which the resulting flow equations are shown by these Feynman diagrams that you see in the bottom left. So this will enable a direct calculation of what are called as dynamical spin structure factors. And the dynamical spin structure factor calculations then allow you for comparison with experimentally observed inelastic neutron scattering on these quantum materials. So the expectation is that to provide a smoking gun signature of the exotic quantum spin liquid phase in 2- and 3-dimensional frustrated quantum magnets via signatures of emergent fractionalized quasi-particles. So what you see out here is an example of one particular quantum spin liquid material candidate, lead copper tellurium oxide, which is based on what is a hyper-Kagome lattice. And you see the inelastic neutron scattering spectrum of it. So these are the type of spectrums which are modeled by these kind of formalisms. So you can see from here generically that the theory and experiment go very hand in hand in this particular business of quantum materials. You have a theoretical model, you would use it, you would make predictions, and they have to be verified by experimental findings. So finally, I'd like to go over to the kind of work I'm interested in. I work on, again, various emergent orders observed in these quantum materials. My interest lies in the microscopic origin of ordered phases like spin ordering, charge ordering, unconventional superconducting state. And I'm also interested in topological phases of matter like Weil semimetals, quantum spin Hall insulators, topological Kondo insulators as they are called. This forum would be, I guess, too short to go over to the entire excitement of all of these materials which are currently very hot topic of research and have a lot of future possible applications. But I could just quite quickly tell you that one or two examples. For example, if you're talking about quantum spin Hall insulators or these topological properties of it, then some of these materials, due to their non-trivial topology, can host a type of particle, are predicted to host a type of particle on their edges called Majorana fermions. So these Majorana fermions can be observed, for example, if you were to do one of these STM, scanning tunneling microscope experiment, as a zero energy state showing up near these edges. So the presence of these Majorana fermions, they are exciting because it has been shown theoretically that these Majorana fermions are decoherence free. That means they are not destroyed by disorder in the material, which is naturally there in most materials. So the absence of disorder means that these materials could actually potentially be exciting development if they are kind of realized kind of with a lot more confidence in future as potential applications for quantum computers. More fundamental physics wise, we are also interested in topological superconductors and unconventional superconductors. Again, as I said, that so in many of these Hamiltonian modeling that I do, one of my interests is to look at how experiments can realize or how I can explain experiments with this. So for example, if you look at the magnetic and charge order materials, the blue graph is what is called as a quasi-particle interference pattern, which is essentially observed by interference of the electron waves around impurities. So when the electron waves interfere by scattering around different impurities, they form an interference pattern. And that interference pattern has not only information about the electronic structure of the material, but interestingly, it can also tell you a lot about the ordering of phases inside it, where the entire physics or the richness of what is happening in quantum materials lies. It also can be used to derive superconductivity. And also, in fact, the right picture that you see out here is showing you edge state physics in a 2D topological insulator. At the edges, you not only have the possibility of what are called as Majorana fermions, but generically the edges can also behave like 1D material and can show another exciting form of matter, what are called as Luttinger liquids. So all of these areas, including the work we are doing on diamonds, is within the scope of our center. And we look to probably as a team discover many new exciting stuff. Thank you, Professor.
Thank you, Shantanu. Thank you very much. And now we move over to my colleague Shiva Ramakrishna's work on X-ray quantum photonics.
Yeah, thank you, Professor Rao, and to the IRIS webinar team for giving us an opportunity to showcase the ongoing and prospective activities of this wonderful team I'm fortunate to be a part of. Within this team, we have the sort of final vertical, which is themed X-ray quantum photonics, where I have the pleasure of working with colleagues from this very institute itself, right from Professor Rao, Professor Vidya Praveen, Professor Arunachalam, who is a colleague in mechanical engineering, a specialist in thin forms of diamond, Professor S. Satyan, and several others, including colleagues who just showcase their work on theoretical physics. One half of the bright universe is matter and the other half is light. So when light and matter come together, you indeed have physics which is very lively and exciting. This physics essentially spans from very short wavelengths, but also goes into very small wavelengths called X-rays. And God forbid, if we ever need to probe what is inside our body and look at maybe a problem in a bone or something, we immediately go to the doctor who first prescribes an X-ray, or now in more modern times, CT scan imaging. But also it's very popular to get MRI images, which my colleague Professor Vidya Praveen alluded to, and it is a spin-based technique. So my colleagues, Professor Panchanan Kuntia and Professor Rao, for example, are experts in spin, as also theorists, Professor Yasir Iqbal and Professor Shantanu, as we saw. So all this sort of plays out in a very synthetic form, like this plus shape theme shows here. We have X-rays, we have photonics, photonic structures, and so on, coming to realize photonic devices and quantum photonic structures as we are seeing. And as we move on in the next view graph, it's deliberately repeated to really bring out the coherence in our group, which involves colleagues who are actually taking advantage of imperfections or defects in materials, as they're called, in order to realize some very unique quantum properties. We have very sophisticated techniques in our group. We will hear very soon about atom by atom imaging, manipulation, and even control in the spatial dimension. But then we also have the temporal dimension, which is very important. So we can, in this group, uniquely control space and time aspects of various things that go on, and in particular defects. So one way is to use very short pulses and in a very minimally thermal way create defects, which essentially you can think of as origins of color in materials very prominently, like our favorite diamond, but also another very prominent material which this group has a lot of research invested into, which is zinc oxide, where, for example, we demonstrated in the left part of this figure that we can indeed control the emission by synthesizing these nanoparticles, ablating them with very short laser pulses. But then what is all this if we cannot couple the nanoscale to the macro world? So between the nano and the macro, there is a micro world. So microstructuring is indeed important to bring out the nanoscale properties onto devices and the such. This is really enabled by laser structuring. And in this view graph, we present the sort of essence of X-ray quantum photonics, which is one of the unique features of this group. And this is work that we do not only in our own lab with tabletop femtosecond lasers, but this opens out a window from extending from our lab into international facilities, which we listed at the bottom. So students trained in our lab, especially, they are now capable of doing research at world-class facilities like the Electra synchrotron in Trieste, Daisy in Hamburg, where we are currently engaged in performing a beam time, and also the European XFEL. And we have a prospective collaboration with the Soleil synchrotron in France and the Eli beam lines in Europe. So a couple of representative results are here. On the left is the theme of these experiments, where we take angstrom or nanoscale matter, which are in free jets, and laser pulses from all the way from near infrared spanning up to the X-rays can be focused onto these in order to realize correlated and collective dynamics. As the right panel here shows, we have this very strangely shaped spectral peak, which has a maximum and also a negative dip. So this is textbook atomic physics, but then there's a very ubiquitous phenomenon called the Fano resonance. So this is just a sort of benchmark result from our work. Physicists in the audience will recognize the importance of this kind of spectral interference. We do this not only on very tabletop materials. We also do this in perhaps the only nanoscale superfluid that we have in our hands, in the form of aggregates of helium atoms, which are called helium nanodroplets. But once again, this is probably something more for a specialist to look at. And at the very bottom right, you see rings on a blue colored view graph. So these are angle resolved and time resolved photoelectron spectra, revealing the internal structure of materials and matter, not just on the spatial scale and on the energy scale, but also we do this in a time resolved way to get information about the dynamics. In the next view graph, we have essentially an internal view of the same system, which produces these unique quantum fluid nanoparticles. So we have a cryogenic source from which you supersonically expand, just like supersonic, say, aircrafts. But here, the people who are flying are nanoscale cryostats. These are helium clusters, and these have millikelvin temperatures, and they can dissolve into them or attach onto them several other species which are held in a vapor form in the doping cell. So now we have cooled down any sort of atomic or molecular aggregate to millikelvin temperatures, and then where the arrow is just hovering, light pulses impinge on this, and we create release electrons and ions which are imaged. This is a bit like an electron microscope, except that we actually don't image them in the spatial domain, but we image them in the momentum or energy momentum space. So we get information about this, as the bottom little graph shows. We need to run some inversion algorithms and so on. Again, it's a matter of detail, but this just showcases the ability to probe matter on fundamental angstrom resolution spatial scales, and with natural time scales which go down to the femtosecond and also the sub-femtosecond or attosecond domain. So as I earlier emphasized, the next view graph essentially is to show to us a little video which if it plays out, will essentially tell us, give us a view of the facility called unique world-class facility, which is the free electron laser in Hamburg. So probably it will play out on Professor Rao's screen. If we have any challenges, we could also play this video out at the end of this presentation from another source.
Yeah,
So
probably
let's just give this a second. Yeah. So this is essentially to showcase the world's first X-ray free electron laser, which is present at the German Electron Synchrotron Center in Hamburg. So our students come here and in very short but very intense spans of time perform experiments with leading researchers and scientists in the world. It's a truly magnificent collaboration that we are often happy to be a part of. In the initial slides, we saw visiting faculty to our department, Professor Marcel Mudrich from Aarhus University, and much of this research is done in a sort of coherent collaboration with Professor Mudrich, and also under the auspices of the Max Planck Society, where I have the pleasure of leading an effort with Professor Thomas Pfeiffer, who's the director of the Max Planck Institute for Nuclear Physics in Heidelberg. The next view graph essentially shows to us the facility that we have in-house at IIT Madras, where we have a similar velocity map imaging spectrometer, and this is where our students get trained. So this is the intellectual gym that they go to and strengthen themselves and perform their own experiments here, as well as take their skills onto world-class facilities. And I also have the immense pleasure of mentioning my colleague, Professor G. Arvind, who's an expert on AMO science and electron spectrometry. So he's also a part of this group and a wonderful collaborative colleague. Just to give you a bird's eye view of the kind of processes that that demand that we investigate electronic phenomena on an angstrom and femtosecond or sub-femtosecond time scale, it may not be super important to know all the details of what this view graph shows, except to realize that when a photon flash, which is the little black flash, is incident on this host dopant system, the host is helium, and the dopant could be typically any set of like atoms or molecules. A photon is absorbed into this aggregate, and then a whole slew of energy transfer processes take place. One can ask, for example, what happens when radiation, ultraviolet radiation, is impinged on us? We get a tan in the skin. If it's just a tan, it's okay, but these radiatively damaging processes actually can be quite detrimental at times, but they are also used in cancer therapy. As we know, radiation does damage. The more and more we understand the physics of this very intricate, complex process, which happens not only on angstrom time scales, angstrom spatial scales, but also goes across hydrogen bonded networks, which is water, which is what mostly our body is made up of, we will have better and better control over these processes and can develop tools which have therapeutic and hence societal applications. It is very hard to imagine that when I go to a hospital, it is and see maybe patients getting such therapies, it is actually fundamentally quantum processes which underlie the physics and the technology of these things. So for this and more, quantum X-ray photonics is indeed a very important facet. And as we see in the next view graph, we have essentially in this center world-class research going on, emerging from India but connecting to the rest of the world, emergent quantum materials. All of this is sort of based on a platform of a very solid platform like Diamond, and we can tinker and manipulate on atomic scales. We can tinker and manipulate on femtosecond time scales. So indeed, there is not only plenty of room, there is also plenty of time at the bottom. So we exploit all this. And on that note of summing up all this, I hand this over back to Professor Rao, and we will continue with our webinar.
Thank you, Siva. Thank you very much. And before I hand over the session to our moderator, Professor Werner Paulus, I need to say a few words about him. Professor Werner Paulus from the University of Montpellier is an expert in X-ray crystallography. He's a long-standing member of the European large-scale facilities like the ESRF. These are very exciting facilities to probe atomic level structural aspects. And you see this ring ESRF, European synchrotron facility located in Grenoble. And he's also a regular member of ILL, Institute of Langevin, located in the same place. I'm not going to go through all the accolades that he has received in all these 40 years of his research and teaching career. One of the important aspects of what he has done in recent times is He was instrumental in getting the Erasmus Mundus master's program running between four European universities very successfully for the fourth time in a row, which is very rare. And this program is called MAMA-SELF, Masters in Materials, Exploring Large-Scale Facilities. Exploring large-scale facilities is very essential for studying materials. And we are also very happy to note that a large number of our students in the last 15 years have gone to do masters and PhD and worked in various European labs to get trained in these large-scale facilities, which is going to be very useful in future for us when these people come back and start their own research careers in India. So with that, I would like Professor Werner to now give a summary and moderate the session.
Okay, thank you very much for this nice introduction. There are many things which need to be said. So we have heard a lot of very interesting things, giving a lot of opportunities, research opportunities. And as a moderator, I have problems to stay moderate because there's too many things to say. So just let me try to resume a little bit the most important things. So we understood that these research activities we have seen are all part of a very competitive field. And they give rise to a lot of technological applications. Even the fundamentals of all these effects are still not understood and need to be explored. So I will try to resume a little bit the most essential ones, but before I try to analyze this, maybe just a word also on these kind of webinars. I like this idea very much because, of course, they are addressed to scientists and give a very short resume what kind of research activities are done in the research center. But I think we have a lot of students in the audience and probably future students also at IIT Madras. They're listening today. They want to get an idea what kind of science is done and how they can get involved in this. So there are many aspects. So you need to, and probably you're also interested to see what kind of things are required today, how to enter all this science and how to successfully continue studies and scientific projects. So from the few questions which I already saw in the box, there are many basic aspects which seem to be interesting for the students and they need to be understood. And this is the big problem. Because when you hear material science is physics, is chemistry, is material science by itself. We have heard words like long range, short range ordering, we have spin ordering, we have charge ordering, we have dynamics, even in the femtosecond range, we have magnetism, quantum spins. So you see, these are a lot of aspects which are important and which need to really be understood if you want to have success in this field. And there's one point which makes different all these things we have heard. So you have heard something about diamond. So you say diamond, this is so old, there's nothing new to discover anymore. This is not true. Because if you dope the diamonds and if you create defects, so you create something which gives new physical properties. And just a word also on the defects which you introduce into solids, this is very different to molecular science. Molecular science, if you have a molecule, it's nicely defined. In solids, so all the physical properties, they are governed by the defects. And this makes these solids totally different compared to molecular things. So here the defects and the defect structure, they become not only important, but decisive for the properties. And it's a fight always for the researcher to put things of the material into the good direction, to understand them and to go ahead and make them also available for technological applications. So all this, what we have heard, looks very exotic, probably needs to be more detailed. And I think for this reason, these kind of webinars are perfect. So you see also, this is not only a research aspect, but which is targeted, but also essential the teaching part. So if you are working on cutting edge materials, it's very important that you are able to synthesize them correctly in a reproducible way. So what we have seen is the diamond thin films, they are made by the CVD method, which looks rather simple, but which is not. Because if you want to realize good samples and in a defined way, in a reproducible way, So that's extremely demanding, needs a lot of knowledge in chemistry and crystal growth, in the physics which is behind the thermodynamics. So all these are fields which you need to know when you really want to be successful in high-tech materials, especially in the thin films. And also you see that together with the characterization, the synthesis makes a nice symbiosis which you have to master. And there's another aspect also, and this is theory. So what I have seen, what you presented from your lab, you have the synthesis, you have the characterization methods, and you have also theory. Theory is very important also to stimulate, understand the compounds, but stimulate also to make new aspects, to develop new aspects, and to go ahead with the together with the characterization to optimize these kind of materials. So I think it's a very nice symbiosis between synthesis, characterization, and also theory, which is in one lab. And this is rare. I think this is really, I can give you a compliment for this. And you do not have this in many institutes. So we have seen structure, physical properties, theory so far. So that means you need to have competencies in what? In chemistry, in structural characterization. That means crystallography. There's a big field which you need to know. And this is not only to know how the structure is organized, but also how to characterize this. And then this synthesis influences the microstructure. We have seen different microstructures also for the diamond. So the microstructure together with the structure makes the properties. And once again, this is defects, how defects are organized and how you can organize them, how you can modify the compounds. So that's an important aspect. So this is also, of course, you cannot get this only if you are only chemist, only physicist. So this needs really a collaboration. And I think this is also the richness which we have seen in this project. Maybe I can also underline another aspect. So we have seen the characterizations which are possible in the lab. And there are some characterizations which you have also seen. So we have seen the outstation in Hamburg at the free electron laser. So this is a sophisticated characterization which happens, which we call large-scale facilities. So large-scale facilities is what? These are synchrotrons, these are neutron scattering methods, and they are only available either at nuclear research reactors or spallation sources or synchrotron instruments. So we will come back to this, but before maybe just a small comparison also from the diamonds in terms of the electronic properties, which we already have heard from correlated oxides. Correlated oxides had made history. Everybody is using this, even maybe without knowing this. So just to tell you, if you have correlated oxides or magnetic oxides, there was an interesting study some 30 years ago. So to couple ferromagnetic and non-ferromagnetic or non-magnetic layers, and depending on the spin orientation of adjacent magnetic layers, you can get what is called magnetoresistive random access memory. So everybody is using this. You don't really know, you need not to know how this works, but it's a revolution in terms of technology. So there was a Nobel Prize some 20 years before on this field. And just also to say that understanding the magnetic properties in the materials, in a different microstructure, in a different macrostructure is important and gives rise also to new tools to access new materials. So what you have also, you have understood that these samples, which are existing as a thin film, so thin films are not very thick, so they are very small. If you want to analyze them, that means you are always searching in the background for signals, and not only for the magnetism, for the structure. We have heard about the defects. If you want to characterize properly the defect structure, you will probably also come to defect ordering. So large-scale facilities, which we have heard before, they play a key role in all this analysis. So what we can do today is we can characterize not only nano-sized samples, they give a weak signature, but sufficiently enough at synchrotron sources because of the brilliance of the synchrotron sources. So these kind of instruments you cannot really compare with lab instruments because the brilliance is several orders of magnitude higher than what you can achieve in the lab. The problem with these large-scale facilities, so you cannot just put them in the cellar room or even on a campus because a nuclear reactor or a synchrotron is just too big. and even to run this needs special requirements. So already also special knowledge. So this is a big thing. And now in the world, there are a lot of synchrotrons. There are some neutron scattering facilities, and they play a very important role in the characterization for all material science. So for us, this was the reason also to create already in 2007 a special master, which is Master in Material Science Exploring Large-Scale Facilities, and which is covering exactly this aspect. So accessing large-scale facilities is not easy because the instruments are quite complex and usually only specialists go. This was one of the reasons also to create this master. And just today, we had the last exam of a 2-week summer school just dealing with large-scale facilities. Means we have a summer school, we explain to our students how this instrument works. And that's a very dedicated, specific organization. So you learn what is a neutron, how you make a neutron, what you can do with neutrons, how you can use them to analyze magnetic structures. The same is also true for synchrotron radiation. So synchrotron radiation is a fantastic tool because you have such a brilliance, you can analyze so small particles now. And it's fundamental to access structure, nuclear structure, magnetism, spectroscopic properties, inelastic electronic configurations. So that's a really fantastic tool, and you need to know this. And this master is dedicated to teach all this at the master level. So I think there's no other master, or really not, to teach this. It's an excellent opportunity. So I say all this not just to make the publicity for our master, but also to say that this master is very nicely related to IIT Madras. I'm not sure you can see my screen. So the IIT Madras is partner in this master, and we are always very happy to have Professor Ramachandra Rao with us. He is teaching actively in this master, and as he already said, there are many students who came already to participate to this master. It's not only a participation, because this is also a master which has the label Erasmus Mundus. I'm not sure you know what are these Erasmus Mundus masters. They have grants from the European community. The grants are very important. So these are grants for master students. It's more than 1,000 euros per month. And I think it's not only attractive because of the money, but what you can learn on this. So I think on top of what we have seen from the laboratory and the project qualities, which you explained in the different talks, I think the teaching aspect is a very important one, because you as a student, you want to see what are your possibilities to learn something, to get trained on this. And you have already seen also from the instruments, which were on some pictures, which I have seen, these instruments are quite complex. So in order to understand them and to go ahead with these instrumentation, you need to get trained, and this is not done, let's say, in 5 minutes. So you need something, you need also experience in this, and you need the lab, which is experience in the field, in order to give you the good education in using all this. And as a combination with large-scale facilities, I think this is a very promising perspective also, in order to proceed to make new compounds, to characterize them also in the good way. Because if you do not have the good answer in the characterization method, and also in the quality of the sample, then you can go in the completely wrong direction. So all these aspects are very important, and I'm very happy to have seen that these things are nicely organized in one lab. Huh? So you have many things in one lab. I think it's a very important aspect. So maybe this is just to tell the students that there are many fields which you need to know in order to characterize samples, the structural one, the spectroscopic one, the electronic properties. So that's a lot of stuff to learn. But it's fun also, because if you understand all these properties, then, and if you digest it, then you can come to innovative aspects. And if you want to go for new materials, innovating science, you need to go through this. So this is your homework to do. It's not only for the teaching aspect, but as I have seen also in IIT Madras, during the teaching, you have also programs inside the lab. And the combination of this is, I think this is the success story which you need in order to go ahead and experience what you have heard in the lectures. So I have a lot of questions. Maybe we can just start with one of them. So resolution at atomic level. So I think that's an important thing. And what we have seen also is the atom probe tomography. I think it's a very powerful method, and probably not everybody has understood what it is. Maybe somebody can say something about this, because this is interesting for the students, and also what you can learn from this, and what you need to understand all this.
Sure, thank you, Werner. So this is an extraordinary technique. IIT Madras can boast of having it as a national facility. And we have one of my colleagues, KG Pradeep, who is an expert in that. So I'd like him to now talk about this wonderful facility and what it can do.
Yeah. So thank you, Professor Limazar, and thank you, Professor Werner. So you started with the interesting question. So as we know, as you already elaborated, defects are one of the major sources of properties in materials. If you understand defects and their associated chemistry, I think we will be in a position to understand the material's behavior in a much better manner. So to give a brief idea of what this atom probe tomography and what it can really do. So my group basically works with correlative microscopy, where we try to combine different microstructural aspects together with their local atomic chemistry. So that means you can see in the current schematics, for example, of a magnet of samarium cobalt based, you see a microstructure as a function of processing and how the microstructure evolves together with the defect structure. So in the atom probe tomography, you can nicely therefore map the local enrichment or local partitioning of these chemical species. For example, copper in the orange color and zirconium in the purple color. They form nice nano platelets if it's in an ordered way, or it's a form of globular bulk clusters if it is in a disordered way. So this already gives us the first fingerprint of how the defects are organized and how this organization is changing the magnetic behavior, as you see from these ordered defined structure and the hysteresis loop associated with it. So one can directly connect the microstructural features with its properties in a straightforward correlation. So coming to the center's objectives, if you now go back and take the, for example, a nanocrystalline diamond thin film. Now we have done this kind of a characterization, so we know it's a diamond. So if you now look at in the, let's say in a reasonable core scale, this is a thin film image obtained in an electron microscope after it has been prepared, for example, with a focus ion beam milling to get it electron transparent. So the first image starts with 1000x magnification. That means if you magnify something at 1000 times than what your eyes can see, this is the film that you see. Now, if you now go a little bit higher in magnification, you start revealing too many things. That means in the bright field image, you start seeing the darker contrasts, which are those defect sites, which is approximately, let's say, 10,000 times magnified from what your eyes can see. Now you will be able to identify there are locations like defects, like stacking faults, and there are other clusters of defects together, which are bright contrast in a dark field image or high angle dark field image. Now, even if you want to know further details of this defect structure, you can go even higher in magnification. That means you can now try to resolve the stacking fault even in higher details. So now we increase the magnification by 15,000 times, you see something more. You increase it 25,000 times, you see even better. Now we are getting close to a situation of revealing the details of the defects itself and its atomic organization. If you go even further higher in the same region, let's say by at least 75,000 times, then you see these nice local twin domains. And now you look at that similar magnification, then you can now distinguish this image containing a lot of these local variations in orientation, like means local segmentation. And even within these segments, you will be able to find this nicely coordinated structure, which you can now combine with the simulated, let's say, 110 orientation of a diamond film. Now, in one of these regions in the hexagon, if you enlarge even further, that means we are crossing 1,000,000 times magnification, we end up seeing these nice hexagonal structures, because the objective is to know where are those NV centers and how these NV centers are basically made of. Then you will be in a position to map those perfectly crystalline regions, which are these pure hexagons in the 110 orientation. Possibly some are now replaced by nitrogen with carbon, so carbon with nitrogen. And there are locations where you can see there are these missing bonds. That means one atom missing from its ideal lattice position, and therefore it tends to create a vacancy at that particular site, which is what you can see here. So now the question is, if you have this vacancy and if you have replacement of carbon with nitrogen, when we dope nitrogen into a diamond, where is this atoms sitting? What is their local chemistry? And how this local chemistry plays a role in the properties that we are expecting. So therefore, that means we are at the end of the limits of electron microscopy. Now comes the atom probe tomography, if you really want to identify where are those atoms. So now this is a atom probe tomography data, which shows only for the nitrogen atoms, just to give a clear impression. Now you see here, there is random distribution of nitrogen atoms everywhere. And if you look at the length scale, these are all in a few nanometer range. Now within this region, we are able to identify with certain concentration threshold an accumulation of nitrogen atoms in localized pockets, which are these defect sites enriched with stacking faults and dislocations. So you can now see there are a lot of these nitrogen atoms being clustered in a local region, which is all happening because of the presence of defects, as we saw in the electron microscope image. So what more we can do with this? So we can now select specific regions out of these clustered domains where the nitrogen atom gets accumulated. And now we can see in a highly magnified view, a three-dimensional distribution of the nitrogen atoms in the matrix, as well as clustering of atoms into local defect sites. And furthermore, we'll be able to even quantify how much of these nitrogen has gone into the defects, which are primarily responsible for the behavior or the conductivity of this diamond at, for example, with respect to your nitrogen concentration. So one can even measure how much of nitrogen is part of your matrix of diamond and how much of nitrogen has gone into the local defect sites with their three-dimensional morphology. So we are resolving individual defects at the angstrom level. We are able to see individual atoms possibly in their ideal lattice positions, and we are able to quantify how much of these species are going into these defect sites as well as into their matrix. So this is the speciality of the technique, that it can really take us to an atomic level and where we can resolve the defect structure and their chemistry at the same time in a correlated fashion. I hope this possibly gives the direction of where we can head into these kind of quantum materials and understand their behavior starting from the microstructure point of view.
Yeah, thank you very much. Very impressive. Huh? And just in regard of this, now we discussed the synthesis. So we have seen a film where you made these thin films. My first question would be how reproducible this is, and can you control the kind of defects and defect distribution just by the synthesis method? I think this is an important aspect.
Yeah, so this is so impressive. Probably the first group to have seen this, the complete hexagonal, the 110 plane and a missing atom. This is really remarkable, no? That's a kind of imaging technique that you need in order to understand that you of course you go and see. One is to identify what that missing atom is. That's the next step, and but of course, from what I understood from Pradeep's work is we certainly have nitrogen everywhere. So the missing atom could be a nitrogen, and what you're seeing there could be an actual envy center. So it's quite exciting.
Okay. So maybe there's one question which comes up many times. So this is concerning the wake shield facility. Maybe somebody can comment on this.
Can you repeat it again?
So I see some comment. Please comment on the wake shield facility. Maybe not. If not, then I come back to my question before, because you discussed the superconducting properties. So now you have different grain size, and the grain size is directly influencing also the superconducting properties. So if you want to go ahead to make devices out of this, means wires or fields or whatever, so you need to control the nanocrystalline structure. So that means the microstructure, even the nanostructure.
Yeah.
Is this possible, and how this influences the physical properties, especially in terms of the magnetic field shielding? No?
Yeah, it is possible. So that's going to be the next phase of our work. as far as superconductivity in diamond is concerned. We are also going to set up a microwave plasma CVD. What we have is a hot filament CVD, as I explained in the beginning of my presentation. So we're going to get a microwave plasma CVD, which can be used to realize, electron grade diamond. So that completely eliminates all other possible dopants or other possible impurities that could go into the lattice. So we start with a pure diamond lattice and dope boron, nitrogen especially, because if you want to see the kind of the experiments that my colleague Praveen has talked about, you need a pure diamond with NV centers in them. And of course, the big challenge again is the crystallography. Getting NV center is one thing, and getting these NV centers in an aligned fashion is the other thing, right?
Exactly.
So, that'll be our focus. And we also have our colleagues who would work on diamond structures using these single crystal growth, single crystal membranes grown using the microwave plasma CVD. So I can ask my other colleagues to elaborate a little bit on that. I think, yes, this is also going to be a very interesting aspect, the engineering and technology aspects of what we plan to do. So it's going to be all the way from atomic level defects to understanding defects to and making them as useful quantum emitters, single quantum emitters, and then you look at those emergent materials and from what our expert theoreticians, theory colleagues are doing.
Yeah, sorry, Sir, I just missed. I was in the mute for some time. I missed that one.
Yeah. So we'll be 1 minute, Satyan. We'll be probably making some of those phases that our colleagues have talked about, and then the engineering aspects also we feel that are absolutely essential and important. And I request my colleague Satyan to talk about
Sure. Yeah. So MSR was talking about creating different structures in diamond. Of course, once you grow the crystals using the microwave plasma CVD techniques, we can use various ways to structure the diamond. We can chisel it. We can polish it. We can so for example, we have facilities for ion beam milling. You can use lasers. Siva has already talked about lasers before. And people like me with more of a mechanical background, we can come and try to do some, even a mechanical polishing kind of techniques to create very thin films. So they make the grown layers even more thinner, for example, and see what happens. So the various ways to chisel and structure this diamond into interesting microstructures and nanostructures that can probably have interesting properties as well. Yeah.
Wonderful.
Over to you, MSR. Yeah.
Thank you, Satyan. And I would request now Dr. Arun to talk about the device aspects that he plans to do with these diamond structures.
Thank you, Professor MSR, and good evening to all of you. Here we have seen the exciting properties of diamond and its application requirement. Now, when a mechanical engineer join with the physicist, what we can see is we can convert the lab scale product to the market, and that's what we currently doing it in terms of realizing this into a product, and we already into the business, and where we have made different structures for diamond in microcrystalline, nanocrystalline, and also we have tailored the graded layer architectures of diamond coating for many applications, mechanical applications, typically for cutting tool, for improved efficiency, as well as for reaction bonded silicon carbide mechanical seal fields for oil and gas applications. And also when it comes to single crystalline diamond, now we have microwave plasma for making the single crystal diamond. There are two kind of approaches you can follow. One is the bottom-up approach and another one is the top-down approach, where you have the crystal and then you apply cutting, polishing and grinding, and in order to convert your diamond wafers to membranes, and then you nanostructures, and you wanted to create patterned arrays. But I mean, dealing with diamond is very, very difficult because its chemical inertness of diamond cannot be make it the hurdle for creating diamond structures in a larger scale. And can I create the diamond wafers to replace silicon? And that is the kind of questions we are trying to answer in this quantum center. In a bottom-up approach, we wanted to create this nanostructures and patterned arrays by creating alumina membranes as well as the titanium oxide membranes, over which we wanted to grow this diamond to create the patterned arrays. And one such application we have exploited already, and which has got an award from our Dare to Dream thing, is the underwater acoustic sensor using diamond as an windows for protecting the system from the corrosive environment of seawater. And also we can the diamond can be utilized for many applications. One of the greater application is because of the high thermal conductivity of the diamond, we can use this for high power electronic applications as a device, and where the heat dissipation is going to be very high, as well as because of this exceptional properties like biocompatibility, we can make use of this for as a sensor for biomarker sensors. And also we can make this for quantum metrology, one of the key application where we can make use of this for understanding the material at the quantum atomic level by using the quantum metrology. So the main challenges we can talk about diamond is the material on par excellence, where we have plethora of applications in various fields. But how to actually fabricate this, how to convert this the diamond into a product for specific applications, and it involves engineering to be applied to convert this into a lab scale diamond to a product level. And that's what we wanted to actually apply here.
Thank you very much.
Maybe another aspect. So we have heard something about the synthesis. We have heard something about the characterization methods. I could imagine that you probably think about more theoretical aspects. That means combination of these kind of layers with semiconductors or insulating layers. Where does the theory in this field go, at least for the moment?
Yeah, sure. So we are also quite excited always to discuss with a very venerable senior member of our team, Professor Bhaskaran, well known for his theoretical work in superconductivity with Phil Anderson. I'd like Professor Bhaskaran to talk about the theoretical aspects of quantum systems.
Thank you, Sir. It's a pleasure to be listening to these exciting presentations. So I'm very happy to be part of this very young and dynamic team. And history shows that whenever different experts join together with a single aim, miracles happen. So I wish the team all the best. It's really a wonderful team. So having said that, I just wanted to say that Professor Werner Paulus's question about the role of theory, I think the role of theory is there at different levels. And people like Yasir and Mukherjee and myself, we try to understand, for example, mechanism of superconductivity in boron diamond. And is it possible to increase the TC, let's say by nitrogen doping or some other doping? Or can we think of some replacement of diamond by, let's say, a piece of stone, a grain of sand, because that's also hard. And there is plenty of that. So is it possible to look for some alternatives? So now there are also theory at the level of what Professor Arunachalam was pointing out, and in terms of building architectures and so on. So I think we need some more support, but definitely microscopic theory seems to be playing very important role in understanding correlated systems, because again and again we are forced to meet correlated systems in this game. So, but I'm very happy that this team has theorists and experimentalists and of different type and engineers. So I think it's really fascinating.
Mm.
And since there are lots of students in the audience, I just wanted to make a general remark. At least in Tamil Nadu, quantum mechanics and mathematical physics are feared subjects by MSc students and so on. But actually the truth is, mathematical physics is very simple, quantum mechanics is very simple. It's simpler than classical mechanics. If only you understand some basic things, you can go a long way, get a PhD and become even a Nobel laureate just by multiplying matrices. The quantum mechanics is so powerful, but the mathematics is not very complicated. So I encourage young students to listen to many outstanding lectures on quantum mechanics. It's available in the web. For example, my own colleague, Professor V. Balakrishnan, is an outstanding quantum mechanic. He has wonderful set of lectures. And there are many quantum mechanics resources. So please make use of them. And it's very exciting. So having said that, I will ask. Thank you, MSR. So I don't have. If there is any specific question, I'll be very happy to.
Yeah. Thank you very much, Professor Bhaskaran, for all the exciting discussions we've been having all these days, especially after we started getting those nice images from Pradeep, the TEM and atom probe tomography images. So certainly we'll continue our discussions in days to come. So back to you, Werner.
Yeah, so, some other questions if somebody wants to ask something. Maybe also the students which are in the audience. I see that the box is almost, they can put something in the box, but I see the box is almost empty now.
Yeah, my colleagues have been answering all those questions. Thanks to them. And probably we can ask my other colleagues if they would like to say a few things, like we have Professor Setupati, Panchanana, Yasir. Anything you guys want to add?
Maybe I just can make some concluding remarks also, because what we have seen is you have a nice symbiosis between experiment and also theory. And you have the characterization, you have the synthesis, and I think the access also to large-scale facilities or microscopic, even atomic characterization is necessary, mandatory in order to explore these kind of fields. So as a type of student, I think what you would need for your lab is you need the chemist, you need the physicist, you need the material sciences. In other words, you need a very versatile student profile. And maybe this is also coming up now. It's no longer the classical physics, it's no longer the classical chemistry, solid state chemistry. So it's a mixture. And I think this is also a challenge for the students to understand that this is really multidisciplinary science, and not only multidisciplinary science, but you have also to go abroad. So it involves many things. And I think there are many challenges inside, not only from the synthesis aspect. So you have to digest this, you have to learn this. This is not something which you will get in 5 minutes. And
which also means that you're this and you're that at the same time, which is quantum.
It must be correlated. So if it is correlated, we have had this word correlated so often, and during the summer school, we had also correlated aspect. So that means it's coherent somehow. And all the incoherent part, this is what I told to the students also, this is in the background. So you have to come out of the background. So you have to be somehow a signal, and you have to see the signals which are in even disordered structures. So almost perfect disorder never exists. We see more and more ordering, more and more long-range ordering on all these compounds. This makes it also challenging to explore them. And today we have the devices to detect this. And some of them are in your lab, some you have to look outside. So I think it's really a challenging aspect of science. And also what students should understand from all this, team working is very important. As an individual, you can contribute, but as an individual, you can never win.
That's good. Thank you very much, Werner. I think I'll just show one, probably a last slide. Yes, so to all those still viewing this long presentation and discussion from our COE presentation, if you want more information, you can always visit our website, QuCenDiEM.org. We also organize these Quant Talks, almost one in a month, on the second Friday of every month. And then we have these quarterly newsletters called Quantum Matters, which I'm sure you'll read and enjoy. So you keep track of Quant Talks and Quantum Matters from our website. You get a lot more information from this website. You also get information about some of the recent publications. And I think with that, I thank Professor Werner and all my wonderful group members, for making this happen. A very cogent presentation. We've been working on it since the last 4 or 5 days. So I'll stop sharing, and I'll hand it over back to Mr. Richu George.
Thank you, Professor. So
sorry for overshooting.
Oh no, not at all, not at all. And very glad that you took all the time to explain so many different aspects of the research initiative, and I think you've covered a really vast range of topics. And just to add on to what Professor Werner was mentioning, we do have the IIID courses, which is very interdisciplinary now. So it's really great that IITM is doing that. We have 12 courses as of now, and then hopefully more. So as I'm really thank everyone in the panel and to all of the participants. It was our pleasure to host you, and thank you for taking to the panel. Thank you for taking all the time and explaining things in such detail and keeping the audience engaged. And thank you to all of the audience. That's all from our end. Thanks a lot. Thanks everyone. Good day.
Thank you very much. Bye-bye.
Thank you. Bye-bye.
Thank you. Bye-bye.
Thank you. Thanks everyone. Bye.
Thank you.